he will talk, or the title is Why Cartan Geometry in Physics, Part 1. Please.
Thank you very much. So thank you all for attending. Welcome to Jean. So this lecture, like the other one, will be introductory in its spirit. I hope that you will come away with some appreciation, if you are a pure mathematician, appreciation from the application of geometry, differential geometry in fundamental physics. So the title of the talk is indeed Cartan Geometry in Physics. We've seen yesterday a talk, for example, applying it to vortices. And people have been applying indeed the Cartan geometric tools to analyze of condensed matter physics. But what I want to say is that there is a more, I would say, more fundamental application to Cartan geometry in the realm of gravitational physics. Right? So I can give the answer right away, and you can leave if you want. So the answer is gravity, right? And the gauge structure of gravity. So for this, I will have first, essentially the lecture will be divided in two broad stuff. So the first, I will, in this hour, I will briefly recall, for those who don't know already, what is gauge field theory, because we are interested in the gauge theories of gravity. And that will be the topic of the second and third lecture. And there we will see how Cartan geometry naturally provides the geometric framework, the kinematic framework for gauge theories of gravity. And so, here I begin. So, very quickly, here we are. So I start with this. Gauge field theory, very quickly. First thing, the kinematics. Physics is given by kinematics and dynamics, right? So the kinematics will be entirely given by geometric structure. And so, to remind or to state, the broad dictionary, which has been discovered or rediscovered in the 70s, right? Mathematicians have been going their own way with the bundle geometry of connection, or the geometry of connection on bundles. And physicists have been developing gauge field theory since the 30s, basically. And in the 70s, they discovered that they have been basically talking about pretty much the same thing. Right, so the first thing, so for example, I will give you the, I messed up my thing, so it should be the reverse, physics and mathematics. Yep. Mathematics. So in physics, maybe you will have heard of the notion of the global gauge symmetry. So what is a global gauge symmetry? When in the mathematical language it is H, the structure group of a bundle, of a principal bundle, P, I will call it P, over M, and of course M will play the role, let's say, space-time. So the base manifold of the bundle plays the role of space-time, of course. I put quotes because it is not quite right, actually, but we will talk about this later in the hour. Then we have the matter field. So what are the matter fields that I call phi, like this? Well, those are sections of associated bundle. So sections of associated bundle, so I guess you all know how associated bundle are written for rho, we call it rho V, representation of the structure group of the bundle. And indeed, we know that there is a theorem by Wigner that explains that basically particles are representation of symmetry groups, right? And fundamental particles are irreducible representation of the symmetry groups. So, okay. That works also for space-time symmetries, but also for gauge symmetries. And those are essentially, not essentially, they are isomorphic to tensorial V-valued zero form on P. Right, so let me write it like this. Tensorial, right? Sorry, it is small. I will try to write bigger. Good. So I continue my little dictionary. Also, you have heard about the Young-Mills gauge potential, right? And you came to appreciate that this is nothing but an enrichment connection on P. I should say the local representative, actually. The local representative of such a connection, right? To a local section. Now, physicists talk about the minimal coupling of matter field to the Young-Mills potential, right? So the minimal coupling is of course given by the exterior covariant derivative that is induced by the enrichment connection. So basically, I should maybe have called it. Let me write it that way. If phi is a tensorial zero form, and this representing the matter field phi. So this is d phi plus phi, right? And here is the piece that is give the minimal coupling of matter field to gauge field. Right? The standard derivative, the round derivative piece, gives just the kinematic term of the field. Then, of course, since there is a Young-Mills gauge potential, there is a Young-Mills gauge field, or field strength. And this is given by. So this has been difficult to find for physicists. That is, Young and Mills struggle to find in the simple SU2 example, struggle to find something that would naturally generalize the Maxwell-Faraday tensor for magnetism. So this struggle. This is given quite elementarily by the geometry. So this is the curvature to form. Which happen to be given by Cartan structure equation. This is not a definition, but still. And in physics, so in the abelian case, you only have the exterior derivative. This therefore would give you the Maxwell-Faraday tensor. In non-abelian gauge field theories, this term is responsible for the self-interaction, the non-linearity of the theory, and the self-interaction of the gauge field itself. We often say that the gauge field is carry color charge or carry gauge charge, meaning that it self-interacts. The gluons, for example, of QCD have color charge, therefore they interact with themselves, and this is these terms that is responsible for that fact. And of course, for example, in electromagnetism, given this definition, we have the notion of sourceless field equation. Right, so in electromagnetism, for example, in Maxwell, this is simply given by beta equals 0 with anti-symmetrization, of course. Right? And this is naturally given, again, at the kinematical level. No dynamics is necessary for this equation to hold by the Bianchi identity. Which again, in the abelian case, give us simply indeed abelian case, we have d omega equals 0, which gives us back the sourceless Maxwell field equations, basically. Now, an important item in the list. Sorry, I will disable some of it. Something that is pervasive now in the physics literature, fundamental at least, is the notion of gauge transformation. Gauge transformation, or gauge group, or gauge symmetry, when those transformation or group live invariant something like a Lagrangian or something like that. Symmetry when we leave something invariant. And so there are a bit of subtleties there, because it can be two things from the geometric standpoint. It can either be the local gluings, so those are induced, so those are essentially. Though, what I mean by that is they are the chain of local trivializing section. So, okay, a local trivializing section is something, as you know, that is simply reflecting the local structure of the bundle, and we usually, to get the local representative of all, I should add local representative everywhere. Right? But to get the local representative, we simply pull back from the bundle down to the base manifold spacetime our various objects, right? And those give us the physical field. Again, I put quote because what is physical is a matter of thinking, actually, right? And so, and the change of such section, right, is via the so those come from the transition function of the bundle, right? Like this. So this is one way to see it. So for example, when we have on one open set I have let's say this. Yeah. So for example, in one open set of the base manifold, I can have a local representative of the connection, so one Yang-Mills potential. On another one, I can have these objects, and of course, you know that both are related in that way. This is the gluing that I'm talking about, and this is what physicists call a gauge transformation between their fields. Yeah. They would say an inhomogeneous gauge transformation because of this piece there. Otherwise, they would call it, and same for the curvature. The curvature on its hand transformed homogeneously as a tensor, a gauge tensor, we would say. So that is one view, but there is another one that arguably is more important, more fundamental, or at least carries a different physical meaning. The vertical automorphism of the bundle. So this one I will call, this view I will call, let's say, that's the passive view of gauge transformation, because indeed what happened is that we have an intrinsic object omega on the bundle, and we simply look at it through different choice of section, right? So, and indeed physicists may well then call the choice of local trivialization section a gauge choice or a gauge fixing. So that's the passive view. It's akin to a change of coordinates when you do Riemannian geometry, right? You have tensor, intrinsic object on space-time, and you look at them through different coordinate patch, and therefore you have a coordinate transformation law. This is a passive view because you don't actively transform the object. You just look at it through different conventional choices. And those are what the gauge or local section are. But the vertical automorphism those are active transformation. So those are those are basically H equivalent diffeos of the bundle that induce the identity transformation on the base manifold, right? So indeed, in a sense, physically, you cannot see those things because this group doesn't act on space-time, basically, M, the base manifold. So, right, and this group, this thing, as you know, is isomorphic to the what is the gauge group. Let's say isomorphic to the gauge group, but I will not curly H like this. It's not an Hilbert space. This is my notation for the gauge group. And this is defined as a set of maps that I will call gamma from the bundle to the structure group, and those are an equivariance given by the conjugation action, right? So this is the gauge group of the bundle, and okay, there is even okay. They can also, given this, they can also be seen as section of an associated bundle, H with fiber H, and through the representation, well, the conjugation action. So, very good. And this view of gauge transformation, I will call active. Because indeed now, what happens is that I am actively transforming the intrinsic object. So let me call psi an element of the automorphism group, right? I act on those in that way, and I can look at both of those guys through a single localizing section, and I will have A. I will have A. So it just turns out that these can be expressed in terms of gamma, the corresponding gauge group element that induce the vertical automorphism. And so I will have a, let's say, a gamma like this, and both are related by, I abuse the notation by calling the local element the same as the global element, right? Just to keep the notation like this. And of course, those two looks locally absolutely the same, and they are therefore impossible to distinguish from the physical point of view, right? So if you have a theory that is required to be gauge invariant, meaning invariant under, depending what you mean, usually you start with this. You ask your theory to be invariant there, which makes sense, right? It means that your theory will be sensitive only to the intrinsic object living on your bundle, right? But you end up, because of this, with a theory that is also invariant under vertical automorphism. And as a matter of physical interpretation, that's richer, right? There is more to understand there. And it's exactly the same situation that happened in general relativity, when you start by saying, okay, I want my theory to be generally covariant, so invariant under coordinate changes, and you say, well, makes sense, because it asks that my theory be sensitive only to the intrinsic geometry of the manifold M that you interpret as being space-time. So you say, sure. I mean, physics should be sensitive not to a coordinate artifact, but only to what is objectively true, right? So it's a kind of well-motivated heuristic principle, or let's say epistemological principle. But then you end up with a theory that is also, therefore, invariant under diffeomorphisms, because locally coordinate change and diffeos look the same. But the inverse of the theory of general relativity under diffeomorphisms is much deeper physically, because it means that M, the base manifold, is not spacetime. The point of M are not events of spacetime, but are the diffeomorphic class of spacetime. Right? And this is the famous Hall argument of Einstein, the point coincidence argument that you struggle with to try to understand the impact of that. And so this is much richer. So this dialectic between those two views of gauge transformation give very different physical, have carried different physical valence, right? Different teaching. So you start with a well-motivated, I would say, epistemic principle, and you end up with a ontological teaching. It tells you what is space-time. Okay, very good. So that's all for the kinematics, right? So basically, already.
Can I just ask a question?
Yeah, sure.
So with the field strength one, what about the divergence of the Maxwell field? You've done the Bianchi identity, but the usual Maxwell equations.
Exactly. Yes, exactly. Well, to the with source.
Yeah.
Well, exactly. That was my next point. So that's the dynamics.
Oh, okay.
Exactly. Perfect. So perfect segue, indeed. I should have thought of that, by the way. Saying, okay, good. We have one half of Maxwell's equation, for example, but we know that we have another half, the source Maxwell equation, and those are not given by purely the geometry, the kinematics, but you need the dynamics. So that's the next dynamics. So that's the next part. Okay. And so the dynamics is the church of Lagrangian, or action. So in classical physics, of course, I limit the talk to classical gauge field theory. The quantum stuff is a whole bunch of issues on its own, but okay, let's just review first classical gauge field theory. So classical dynamics given by field equation. So not the sourceless one, but with source. And from applying applying the variational principle to an action or Lagrangian. So that's where the dynamics is hidden. So field equation as extracted from a Lagrangian action via the variational principle. And so the question is, okay, very well. The question is how you build those. So consider the field space. So the field space, I will call it capital phi like this, and it will be the set of connection or local connection I call A, and for the Young-Mills potential, right? The set of all Young-Mills potential or Riemann connection, okay. And the matter field described by section of associated bundle like this. So the point phi will be something like this, actually. And so a Lagrangian will be a functional from field space to and from M. Okay. So we build this. So the Lagrangian top form on space-time. This is a volume form, basically. Okay, Lagrangian will be a volume form on space-time. And the physical information is in the scaling factor of the volume form, the Lagrangian density. That we call. Of course, could have taken more truly. I could have probably taken the jet bundle of phi, but okay, let me be sloppy like this. So either that way, or could have been also, depending on what you are doing exactly, that could have been the target space, could have been the set of m dimension, basic m form on the bundle, right? Because so I do not define basic, meaning that they are trivial equivariants and they are horizontal, so they descend as a well-defined precisely top form on M. My point is that you can either work directly on the bundle there, yes, or you work on space-time. So yes. So either with a global object, so connection and say tensorial zero form, those, or you work on the base manifold with Young potential in section. And either way, you can build a Lagrangian. You should be able to build a Lagrangian. Well, actually, no. We'll see why it may be complicated. For topological theory, you can do that. For most physically relevant theories, you'd rather go directly there because there are ingredients existing on M that doesn't exist on the model, most notably a Hodge operator. At least if you don't give yourself a bundle metric, you will not have a Hodge. So there are operations that you cannot do on P that you can do on M if you endow M with a metric, which you assume at least tacitly most of the time. Okay? So the question is, fine. Question. How to constrain the choice of L. Right? That's the big issue. You know, how to be a clever physicist is how to find a nicely constrained Lagrangian. And those are often, at least, well, of course there is one constraint will come from empirical experiment, you know, empirical adequacy of your theory, so you have empirical input in the, that comes in the building of L, right? But there is another one, which is prior to that, mainly, which comes from symmetry principle. And those are just key to gauge field theory. Because, and in physics in general in the 20th century, right, but symmetry principle is really the key feature of gauge field theory compared to field theory more general. Okay, field theory would be the geometry of bundle, okay, whatever. But gauge field theory makes, given the geometric setup, make use of symmetry principle in a very important way. And so essentially we have two important ones. So symmetry principle. By the way, I should have said that. Okay, we can write it there. So those symmetry principle. So what it means? It means have the Lagrangian or the action S. Sorry, I didn't define the action. I will do it later. The Lagrangian say invariant under some group of transformation group, right? And these will ensure covariance. Should ensure covariance of the field equation. Field equation under said symmetry group, right? So Einstein looks for, I don't know, generally covariant field equation for the gravitational field. Well, you should do well to find a Lagrangian functional that is invariant under those. Right? This is not how he did it historically. This is how Hilbert did it. But fine. Today, this is the basic assumption. And so we have basically two broad principles. So the first of all will be the, as I told, the general covariance principle. Okay, or general relativity principle. This is more not precise language, but okay, we understand in physics. You understand what it means, and basically, so you ask things to be invariant under coordinates. So basically, it just means you're working with forms. Right, because differential forms are, well, intrinsic objects, or what? Sure, they were done. And yes, often to some part of the physics community, this is what is understood when you talk about Cartan. They think, okay, Cartan formalism, numerical calculus, stuff like that. This is what is understood. Less and less, fortunately, but. And the other one is the gauge principle. this is of course key to gauge field theory. Right. So, and that is key to general relativistic physics. But this is key to the gauge field theory. And this is simply to ask that L to your Lagrangian of your field. So either have trivial local gluings. Again, saying that basically your theory, so this is your theory basically. Your theory will be sensitive only to the intrinsic geometry of the bundle. This is what it means basically. This is how you would translate this principle. Or, so basically so this means that it is basic on P. If you have started to work on the bundle rather than on space-time, you would ask that it is basic on P. Basically, this is what would gauge invariant mean. And this is the same as, okay, I should have go with the other one, but okay. So, yeah. Okay. So, sorry. Invariance under passive. Yeah, sorry, I should have led with that. So, two ways to interpret this gauge principle. You have either invariance under passive gauge transformation, in which case it means essentially that there's trivial gluing, so theory sensitive only to intrinsic object on the total of the intrinsic geometry of the bundle, or it is invariant under vertical automorphism, meaning active gauge transformation. Local version, if you are the base space. Global version if you are on P. And if you are on P, it means that it is basic. Okay. So this is what the two ways the gauge principle can be understood, either in the passive and active way, with, again, the two philosophical interpretation, the two philosophical and physical interpretation that comes with the two dual dialectic interpretations of the two. And so to satisfy the gauge principle, one needs, to satisfy the gauge principle, I will need to build L. Smart thing to do would be to start by using tensorial form, right? And by which I mean H tensorial, right? Transform homogeneous object transformation, transforming homogeneously under the gauge group, or with homogeneous gluing, which is okay. Again, dialectic between those two. From tensorial forms of P. Okay, I should add here perhaps H tensorial form here. And of course I need essentially H invariant, non-degenerate. So looking at the kinematics that we had as tensorial objects, well, good, the matter field are tensorial. The covariant derivative of the external covariant derivative is precisely an operator that preserves tensoriality of form. So fields or sectional are tensorial, covariant derivatives are tensorial. The curvature of the connection is tensorial. So those give us the basic ingredient we will shuffle up to build Lagrangian, satisfying the gauge principle. Right? But we have to bundle them together with H invariant, non-degenerate, bilinear forms on, well, sorry, forms on, so on the Lie algebra of H, I will call the Lie algebra of H like this because I have poor calligraphic abilities, so let me do this. So this basically means using the killing form, or the trace, you often in physics typically use the trace. So you will have killing, okay, something like this. So BH, this killing form force. Okay, yeah. For the algebra from which this is indeed the case, and on the representation space in which matter fields are valued, right, as representation of the symmetry group, and V. So that will be the inner product when there is one, or you find one. So, right, you will have something like this. And so, for example, to give you a prototypical example of things that works like this. So let me write, for example, the Yang-Mills Lagrange. Yang-Mills theory. Well, again, what we will do. So, satisfying the general GR principle, well, we will work with forms. So that's easy. We will take the local representative of the curvature because we want also to work with the gauge principle. So we cannot write anything that depends only on the connection, right? Something like this, a Lagrangian. So in Yang-Mills theory, we have only a gauge potential, purely the theory of the gauge potential at first. So if you want something like this, we will need to use the killing form on the Lie algebra. Okay, so up to some constant beta that we don't care for now. And so you will plug, for example, if you did plug something like this, that doesn't work because it is not there anymore. But these stuff are non-homogeneous objects, so it doesn't work. So instead, you will use as your first guess that stuff. And to be concrete, in physics, for SUN groups, typically, you will have something like this. And I forgot to add something. Okay, I semi-intentionally say it. Okay. So this is the Hodge. You're using the Hodge, so you're assuming that there is a metric on M. So G on M. Tacit assumption. I will come back to this later, of course. But okay. So this is the Yang-Mills Lagrangian, for example. The Dirac Lagrangian, Dirac theory. So it is a section of a. Okay. It is a spinor, of course. I again tacitly don't say much more about this, but it's spinor with value in a representation for the group H of our bundle under consideration. Could have gone the scalar way. Okay. And you will do something like this. Okay. Using this inner product. And so what can you do? Well, you're pretty much free because you can use the spinor will be a tensor object, it's covariant derivative too, so you write something like this. Right? And this is pretty much the Dirac Lagrangian. If you add the famous slash stuff, which means that D slash is basically gamma matrices like this. So with gamma, gamma A, dx mu. Again, I will come back to this object later, the soldering form that physicists use, right? But okay, so that's for the next two lectures. To try to, because of course I didn't say anything about it's for crumbles for the next lecture to be okay. Where those objects come from, actually. They are assumed that those didn't come from the kinematics of the bundle I talked before. Right? So it's a little intrusive object in the building of physically relevant physical theory. Because of course, the realistic model is simply to have L Yang-Mills of A plus L Dirac. So Yang-Mills, Dirac of A psi. Okay. This is a semi-realistic theory already. This is basically one of the basic ingredients of the standard model of particle physics. With only this. Of course, we have a scalar field also. The scalar field is even easier because it doesn't even need Okay, it needs a hot start, sure. But it doesn't need the gamma, it's not a spinner, so less complicated. And the potential, so it's all very easy. Right. And to finish, almost. Yeah, sure. Yeah. And so how you get field equation? So because those are Lagrangian, you should extract field equation from those. So that's easy. You define again we said so. You define the action. Yes, like this. And the action will be the integral of your Lagrangian form on some, either on the whole manifold or at least on an open set, an open patch of the manifold. Maybe a compact one. If you give fall-off condition to your fields, it amounts to compactification, as Rod said yesterday. That's why you can compactify Minkowski space, for example. If this is your Minkowski space, you can compactify it in practice, by giving fall-off condition to your field. And let me call it the D domain, not to conflate it necessarily with the open patch of the bundle. Right? That's right, very good. And so how do you get that? Well, you ask that. So variation of the field, right, gives a variation of the action, and it allows the action to be stationary. And so you have that in the end, it amounts to writing the variation of the Lagrangian as a first piece which gives you the field equation plus a boundary term like this. So what is it? It will be a functional of linear in the variation of the field and some functional polynomial field equation in terms of the field, and the same for the guy that is here. It will be linear like this. Okay, these usually comes from partial integration, this stuff. And these are the field equation. Of course, if you do the variational complex stuff, you will have this is a form of B degree, because this is degree 1 in the variational direction, and this is an n form on spacetime, while this is an n minus form on spacetime, and also a 1 form variationally. And so this is often called the presymplectic potential of the theory. I will not go into this, but people trying to, let's say, extend symplectic geometry to field space often start with that guy to define a symplectic 2 form on field space and do things interesting. Of course, if you want to have a well-defined variational principle, you need to have these 0 at the boundary of D, so usually you neglect this piece. 0 at the boundary of the domain, so you can neglect it, and this will give you indeed E equals 0. And those are your field equations. So again, taking the example we have above, very quickly, so not to bore you too much. Yeah. Sure. Sorry. 2 minutes. Maybe next time. Oh yeah. Yeah, okay, sure. Another example I forget to mention here, which does not satisfy the gauge principle, but which is often still encountered in the literature, and we did yesterday too, is the Chern-Simons Lagrangian. So let me just. Okay, so Chern-Simons Lagrangian, which is given by this expression, I get d cubed or trace ADA plus 2/3 a cubed. This does not satisfy the gauge principle, right? General covariance, yes, but this is not basic on P. This doesn't have trivial gluings. at all, so it is not gauge invariant, but still it's found nice application in physics, condensed matter physics, as we've seen, but also even for some toy model in low dimension, this has been used profitably. And yes, very good. Right. Very good. And so yes, just to give you the example. So for example, so the field equation of your mills and its symplectic potential will be given by trace of delta A star F. So you can do that as an exercise if you want, for example, very easy. But you have these plus D trace delta A star F. Right. So indeed, if you can neglect this, suppose you can neglect this, E equals 0 in trace delta A D star F equals 0. And again, and now important, now since we asked non-degeneracy, well, the thing here was not gratuitous, because this is what allows you to say things, this should hold whatever delta A is. This gives you the Young-Mills equation. D star F equals 0. So this is the Young-Mills equation, sourceless Young-Mills equation, but this answers Rod's question. This in the abelian case, of course, is not abelian. Abelian, this is just D star F equals 0, which is the second half of Maxwell's equation. But in the general case, we have the non-abelian coupling. So very nice. And just to have it for Dirac and Dirac, we have again delta psi plus D of theta delta psi like this, and because I consider in the covariant derivative there that A is not a dynamical field, passive background configuration. So, and this will give me the again up to multiplication, but this star psi plus well, okay. Let me write it like this maybe. Delta psi, psi, something like this. So this is doesn't matter that much, G. Well, okay, it does, of course. For the discussion, doesn't. We should be able to neglect this. This is a Dirac current. It will be important when you couple to a dynamical gauge field, right? But for now, we therefore have that. If you can neglect this, we have E equals 0 means. Sorry. D psi equals 0, and this is. Sorry. Yeah. Excuse me. This is D psi equals 0, and this is Dirac. This is the Dirac equation without mass, for example, obtained quite easily. Okay, well, yes, very good. The last, I think I'm done, probably. Yeah?
What notation are you using there inside the trace on the second last line? It looks like bracket, but I don't think that's what you're using.
Yeah, no, indeed, yeah. I should have, I'm not a fan of that notation. It's just a way to write, because indeed when this is coupled to a dynamical gauge field, there is a trace, you know, yes, the polynomial used is a trace, right? So when I write the full coupling, for example, when I have the coupling of Young-Mills equation, in this theory, the full one, you have Young-Mills equation coupled to the Dirac current actually, or yeah, something that is written, should be written like that, because you have delta A.
So you mean like an alpha product, basically?
Yeah, there is an inner product, and I see the inner product as the trace of the bracket. It needs the Dirac notation and the bracket notation, basically, but more this is different. Okay, I like to write it that way just to have it easily recognizable that the field equation should be delta A of this piece, delta A of something written like that, also delta A with the Dirac current. And so we see that the Dirac current will source the Young-Mills equation. Okay. So I wanted to say something about the Noether charge and Noether theorem, but I will start with this in the first 10 minutes of the next talk to end after that. So for now, this is the overview of the gauge field theory, kinematics, dynamics, symmetry principle. And the question that motivates us now is to say, okay, these objects, we know, these classical theories, we know how to quantize, we know how to, and to compute things with them. And this is a standard model, right, for particle physics. And if we have as ambition to either quantize gravity or unify it with the other three non-gravitational interactions, so weak, strong, electromagnetic, the idea would be to have gravity formulated in the same, even at the classical level, in the same kind of framework, as a gauge theory. So we want a gauge theory of gravity. And this is where Cartan enter the game and give us the right answer. And this will be the next two lectures. So, thanks. Oh, yeah. Oh,
Is there any a priori reason why we may have chosen that Lagrangian for the Dirac theory? Or is it just because that one is the one that gives us the Dirac
of course,
equation?
historically,
Yeah.
Historical development is always very messy and does not go straight to the goal. This is the straight to the goal option, which is this is the easiest Lagrangian you can think of for a spinor, a colored spinor.
I suppose one that gives a non-trivial equation of motion, right? Because you could have just done the inner product with just psi and psi.
Psi and psi, but
Yeah.
psi and psi, I did not write it, but this is just a mass term for the
Yeah.
Dirac equation, basically. So there is no, the point is that you want a kinematics, and
Right,
the kinematics
okay.
will be given by a derivative of something.
Okay.
And so indeed, this is the most easy Lagrangian you can write that gives you indeed a non-trivial propagation object, basically.
Okay.
So that's the simplest possible. But the same for that one, by the way. This is also the idea, so, okay, I want a propagation of some field, the A, and what is the only tensor object in which there is a derivative of A is a curvature. So basically this is the simplest possible Lagrangian you can write that will give you a propagating and self-interacting object due to the where is it? Okay, to the nonlinear piece in the A square piece in the
Okay. We are behind the schedule, so I suggest
Yeah,
we
sorry.
move. No, we started later, so we move other questions for the coffee break.
Yeah.
So let's thank the speaker again.